This work presents a deep reinforcement learning framework to develop a policy for quadruped-agnostic locomotion control. Typically, RL policies are tailored to a specific robot embodiment, and whenever the robot's morphology or dynamics changes, a new policy needs to be trained from scratch. Many quadrupedal robots share a common 12 degrees of freedom design template, which we aim to exploit by training a universal locomotion policy that can transfer to these diverse platforms. Drawing inspiration from meta-RL literature, we train a recurrent policy on a diverse set of quadrupedal robots generated by randomizing the parameters of two commercial robots Unitree Go1 and Unitree Aliengo. For each of the training robots, we designed an RL task to replicate base and feet motion demonstrations produced by a kinematic reference generator. We show that by training our policy across a small number of robots, it learns to control some easier morphologies first, and then generalizes the desired motion to edge morphologies with very different kinematic and dynamic properties. In our first simulation experiment, we test our policy on 40 quadrupeds not seen during training. Our recurrent policy can control all unseen simulated robots, generalizing the trotting gait and adhering to the speed commands. Our architecture includes a recurrent encoder, namely a Giuro cell, which learns general strategies by performing implicit system identification in its hidden state. We show the criticality of this module by comparing our policy with an MLP that receives an input the current state or a history of the last 16 states in action. By visualizing the policies, we notice that the MLP variants can't control some edge morphologies. In fact, they can't track the desired feet height, or they fail to follow the velocity command. In contrast, our recurrent policy maintains high-quality motion. Moreover, the MLP variants always induce a large base rotation. In the regularization reward, there is a term that encourages to keep the pitch and roll angles close to zero, as successfully achieved by our policy. The policy trained using our method achieves zero-shot transfer to 3 hardware platforms, not seen during training. Firstly, it can control Unitree Go1. Then, it was capable to control also Unitree Go2, whose morphologies and dynamic properties are quite different. Finally, without any fine-tuning, the same policy could control the locomotion of Unitree Aliengo, a heavier and larger quadrupedal robot. Thank you for watching.